Welcome to this lecture on recurrence relations. Recurrence relations are a very useful tool for solving counting problems. They are more advanced than the techniques we studied in the previous lecture. But we mentioned them before, remember, when we talked about sequences. In fact, a recurrence relation is a way to define a sequence, A sub I. It's a recursive definition that expresses the generic term A sub n in terms of or as a function of one or more of the previous terms of the sequence, namely A sub n minus 1, A sub n minus 2, and so on, for all integers n as long as n is greater than or equal to some threshold n0. So let's look at an example. The sequence A sub n, or the generic term A sub n, could be defined as the sum of A sub n minus 1 and A sub n minus 2. In fact, this is a recurrence relation for the Fibonacci sequence that we talked about earlier. Now, this recurrence relation holds for any n as long as n is large enough. In this case, n must be greater than or equal to 2. That's because we are going two terms back in the sequence to compute the next term. So, that's the definition of a recurrence relation. Now, when I said this was the definition of the Fibonacci sequence, actually, there's more than one sequence that satisfies this recurrence relation. So, a sequence whose terms satisfy a particular recurrence relation R is called a solution of that recurrence relation. So the Fibonacci sequence that we talked about earlier is really one of the solutions of this recurrence relation. Now remember that the first two terms in the Fibonacci sequence are 0 and 1. Once you provide those first two terms, you can use the recurrence relation here to compute the next term, which is the sum of the two previous terms. So the next term will be 0 plus 1 or 1. The fourth term will be 1 plus 1 or 2. The next term, 1 plus 2, 3, 2 plus 3, 3 plus 5, 5 plus 8, etc. But notice, this is only one of the solutions of this recurrence relation. So for example, if I started with two different values for the first two terms, then I would get a completely different sequence. But that sequence also satisfies this recurrence relation as long as n is greater than or equal to 2. So let's look at one more example of a recurrence relation. This one says that A sub n equals 3 times A sub n minus 1 minus A sub n minus 2. And even though we don't state it here, this assumes that n is greater than or equal to 2. So the question now is, if I give you a sequence, can you check if it's a solution of this recurrence relation? So I'm going to give you several examples now to work on. The first sequence I want you to consider is the constant sequence A sub n is equal to 5. Is this sequence a solution of this recurrence relation? To determine whether this sequence is a solution of this recurrence relation, we're going to compute the right-hand side of this equality, and then we're going to replace each term here by its definition. So by definition, A sub n minus 1 is equal to 5, and so is A sub n minus 2, because for every n, A sub n is 5. So we get 3 times 5 minus 2 times 5, that is 15 minus 10, which is equal to 5. And 5 is indeed equal to A sub n for an arbitrary n. So we just proved that this sequence here is a solution of this recurrence relation. Let's record that. Now notice that this sequence here is not defined recursively. It's defined by a closed form formula. And we just showed that this sequence can also be defined recursively using this recurrence relation. Now, Let's look at a second example of a sequence. A sub n equals 4 times n. Again, we're going to start from the right-hand side of the recurrence relation, and now we're going to replace a sub n minus 1 by what? Well, a sub n minus 1 is by definition 4 times n minus 1, or 4 times minus 4, preceded by a factor of 3. And a sub n minus 2 is going to be 4 times n minus 2, or 4n minus 8. So here is the expression that we get by substituting the definition of these terms. And now we're going to rearrange 12n minus 8n will give us 4n, and minus 12 plus 16 will give us plus 4. So we got 4n plus 4, and 4n plus 4 is not equal to 4n for any value of n. Therefore, this is not equal to a sub n, and as a conclusion, this sequence is not a solution of this recurrence relation. Now let's consider a third sequence, a third example, as a potential solution for this recurrence relation. So let's see if that's indeed the case. So we start again from the right-hand side, and we're going to replace a sub n minus 1 by its definition, that's 2 to the power n minus 1. And similarly, a sub n minus 2 is going to be 2 to the power n minus 2. Now we can just multiply the 2's together to get 2 to the power n minus 1. And then we can factor out the 2 to the power n minus 1, and we're going to be left with 3 minus 1, or 2. So we have 2 to the power n minus 1 times 2, and that's equal to 2 to the power n, which, by the way, is equal to a sub n. So we just proved that for an arbitrary n, this expression here is equal to a sub n, and therefore this sequence is a solution of this recurrence relation. So far we've found two solutions, and here this is not a solution of this recurrence relation. Let me give you an exercise for you to work on at home. Consider this slightly different sequence, a sub n equals 3 plus 2 to the power n, and I want you to check that this sequence, which is different from the previous three, is also a solution of this recurrence relation. Hopefully these examples have helped you get comfortable with the concept of recurrence relations and their solutions. Now let's wrap up this segment with a couple more definitions. First, the initial conditions for a sequence specify the values of the first few terms in the sequence. In fact, the initial conditions must specify the values of the terms a sub I, where I goes all the way up to n0, not including n0 if you start at 0. So remember, when we define this recurrence relation here, we define a sub n in terms of the two previous terms. So this recurrence relation holds only for n greater than or equal to n0, where n0 is equal to 2. So when you want to compute the terms in a sequence that satisfy this recurrence relation, you must first provide the values of the first two terms for n equals 0 and n equals 1. These are the values that we chose when we wrote down the Fibonacci sequence here. Well, these first two values are just called the initial conditions for this sequence. Now, for this other sequence, notice that sequence also was a solution for this recurrence relation, but it's different from this sequence because we started with different initial conditions, in this case 1 and minus 1. Now the second definition is that of a recursive definition. So a recursive definition for a sequence is the combination of two things. First, a recurrence relation, and then a matching set of initial conditions. So going back to our example again, this recurrence relation together with this set of initial conditions is a recursive definition for this sequence. And what do we mean by a matching set of initial conditions? All we mean is that if n0 is equal to 2 in the recurrence relations, then the initial conditions must also specify the value of 2, or more generally, n0 terms. That's how they match. So as another example, this recurrence relation, together with a different set of initial conditions, namely this one, is a recursive definition for this other sequence. So, as should be obvious already from the examples, a recurrence relation has many solutions, as we showed here. Actually, it has an infinite number of solutions. Why? Because there's a different solution for every initial condition that you choose. However, once you fix the initial conditions, what you get is a recursive definition, and this recursive definition uniquely determines the sequence, meaning there's only one sequence of terms that satisfy a recursive definition, but there are an infinite number of sequences that are solutions of a recursive relation if you don't provide a matching set of initial conditions.